Okie doke. This should be recording officially. I did one of these all the way through, whole presentation, with the PowerPoint thingy up, like actually playing, and it didn't work. It didn't record it. It only recorded like the background. So I apologize for seeing, behind the scenes, I guess, of the stuff, but I tried to zoom it out so that it's easier to see. But my name is Reid Williams. I'm obviously in this class because I'm doing a presentation about stuff, and the stuff I decided to talk about today is graphs, as well as an algorithm that I can't pronounce. I don't know why I picked the one that you can probably figure out which one it is, given context. But whenever I think about a graph, I think about, like this guy, like X, Y, plotting acceleration and velocity, things like that, or including Z if you're getting fancy in physics classes, or even like a bar chart, things like this. I got a degree in marketing back in the Disney day, and we used this stuff a bunch, like break-even points and stuff like that, although that's in the other graph. Or even like a Venn diagram. But what we're talking about today is these guys. So this here is the kind of information structure that we're using whenever we're using graphs for this type of data structure. And a little bit of background on what this is. And most of my definitions, if not all, are pulled from our book. It is in the footnotes of the intro to this this PowerPoint, which I'll upload as well. I'm pretty sure I can upload the PowerPoint. But a graph is a data structure for representing connections among items, and they consist of these things called vertices. I don't know what the proper way to do the plurality of that is. And edges. And as you can see from my gorgeous graphics, a vertex, so A, D, B, F, C, G, or nodes is another way that they can be described. They represent an item in a graph. So these are kind of like data points. You can think of them. We'll talk a little bit more later about the applications of this stuff. But it can be a product or just straight up information stored in a database with different links between the information. And those links are E2, E3, E1, E4, E5, E7, E6. Those are all edges. And these edges represent a connection between two vertexes in a graph. And the edges are important, and they can kind of be manifested in a couple of different ways, which we'll also talk about a little bit later. There's a couple different types of these graphs. But in order for two vertexes to be treated as adjacent, so like associated or like directly associated with each other, they need to share one of these edges. So if you're just looking at the graph, you could make an argument that D and F, they look adjacent. I mean, they're to the next of each other and they're about as distant as any of the other pieces of data, but the important info is that they do not share an edge. So D and F, there's no E anything, whereas F and G, they share E7 and therefore are adjacent. And there's a couple different ways to kind of traverse these graphs. A path is just kind of getting from A to G. It doesn't super matter how you do it, but the list of edges you hit would be the path. So if I wanted to get from A to C, I could go E1, E4, E5, and that's a path, E1, E4, E5. But if I want to find the distance between A and C, what I need to do is find the number of edges on the shortest path between those vertexes. So while E1, E4, E5 is technically, one way to get there, it's not shorter. I guess the important assumption here, which once again get into a little bit more in a minute, is that these are equal. E2 is the same distance as E3 is the same distance as E1. So if we keep that assumption, then the distance of E3, E4 is only 2, whereas E1, E4, E5 is 3. Therefore, the distance between A and C is 2, E3 and E5. As I said, there's a couple different types of these graphs, at least discussed in our book. There might be more that I'm unfamiliar with, but there are weighted graphs and there are directed graphs. And you can probably assume, you know, what that means. Weighted is kind of my favorite BT dubs because it explains a lot of stuff, super, I guess, flexible in how it could be used. But a weighted graph, as you can see here, we're kind of going back to that A to C example, or A to F example, we'll say, to make it easier for this. And so the definition of a weighted graph is a graph associates a weight with each edge. A graph's edge weight, or cost, represents some numerical value between vertex items, such as flight costs between airports, connection speeds for your computer, travel time, and they can be directed or undirected, which isn't super clear yet since we haven't talked about what that means. But in a weighted graph, the path length is actually the sum of the edge weight. So it's not just that we're going E3 from A to F, and therefore it's just 1. We have to look at the weight of E3, which is 3. So kind of in the previous example where we were looking at, you know, obviously they're all the same weight, and therefore the shorter number of edges is better. Here, the edge E1 and E4 are only weighted as 1 each, and therefore it would only be a weight of 2 to get from A to F, whereas E3 is weighted as 3, and therefore would take a weight of 3 to get from A to F. Therefore, the distance in this situation, so the shortest distance from A to F, is actually E1, E4, not E3, which is kind of an interesting thing about weighted graphs. Now moving on to directed graphs. Directed graph, similar to all other kinds of graphs, but each of the edges is associated with or assigned or include a direction. So you can see on the top graph, 1 goes to 2, which goes to 3, which can also go back to 2, and then 3 goes to 1. You can't go from 1 to 3. Same with the graph below it. A to B to C to E to F, or to D to B. But if you get to F, you're kind of stuck. You can't really get back to E because of the way that this directed graph is associating itself. And in a directed graph, a path in a directed is similar to other graphs, but starts at a source vertex. So we say 1 is a source vertex and ends at a destination vertex, which would be 2 in this top graph here, 1 to 2. 2, if we wanted 2 to be the start vertex and we wanted to get to 1, we would have to go 2, 3, 1. That would be the only way to get through because of this direction of 2. And kind of an interesting, I guess, like thought problem. I mean, you can kind of think of all graphs as directed if you think of all graphs as having, I mean, if it's undirected, if the direction is just like to and fro. You know, if this 2 to 3 double line was here as well as here, you know, it would be undirected even though you kind of gave directions to those. So another interesting and important concept with directed graphs is that they can have cycles, meaning a path that starts and ends at the same vertex. And a directed graph is cyclic if the graph contains a cycle, and acyclic if the graph does not contain a cycle. So an important point is that the graph itself doesn't have to like be a cycle to be cyclic. So the graph below, where it goes from A to B to C to, you know, that even though it has F and you can't get back to A, it's still cyclic if you go B to B. Same with, 1, 2, 3 above. It doesn't have to be that kind of manifestation. You have to not contain any cycles, essentially, to be treated as acyclic, which makes sense. So it always helps me whenever I'm, studying these data structures and these kind of ephemeral, like broader, more difficult concepts, to think about how they're actually used. Like, what's the point of it all? An easy one, a couple of easy ones are product recommendations or like Facebook friend recommendations. So if you go on Amazon and you buy toilet paper, because we're in a pandemic, it's like a meme from like 6 months ago. If you buy toilet paper, it might recommend in the below either similar products are, toothpaste or plungers, or I almost said plumbers, plungers or whatever, or it could say like similar people bought XYZ. Those are, you can think of you and your purchase as a node, or your item as a node, and the individual or the purchase made by that other individual as another node. And it's like how closely those items or things are related can be the edge, like the weight of the similarity between the two. Same goes for Facebook friends. If you are friends with Morgan, who's friends with Rachel, it might recommend Rachel because you're friends with Morgan, Morgan's friends with Rachel. It might push Rachel harder if you're friends with like Morgan, Joe, Bob, and Alexander, and all of them are friends with Rachel. It's like, obviously you know this one because you have so many nodes in common, you have so many, it might kind of increase the similarity between the two. And from the directed and weighted stuff prior, I like the idea of, it's in the book, if I remember correctly, like a directed node could be a link on a web page. So if you Google something and you click that link, it takes you from Google to the new page. You can't then, outside of using like the back button, there's no link that immediately brings you back to Google. I think a fun kind of project, if you wanted to do these, like maybe Google something and then see how many nodes you have to go through to get back to Google just by clicking on links. Probably not that many, honestly. But those are some implementations of graphs. So there are quite a few algorithms that can be used in association with graphs. As you can see here, these are just a number that we discussed in the actual book. Excuse me. There could be, quite a few more. I assume that there are. And the one we'll be talking about today is the second. I don't know why I picked the one that I can't pronounce, but Dijkstra shortest path algorithm. And I put this here because I thought it was funny when I was making this presentation. Have you ever played the game, 6 degrees from Kevin Bacon, or 7, whatever? We're trying to figure out from like your cousin how they would be like associated with Kevin Bacon. Shortest path algorithms are kind of like trying to find the shortest connection between X and Y, or between you, or figure out who is the closest to Kevin Bacon. Doesn't super make sense, but I thought it was kind of funny. So in this shortest path algorithm created by this individual, it actually determines the shortest path from a start vertex to every other vertex in your graph, in a graph. And for each vertex, this algorithm determines the vertex's distance as well as predecessor pointers. And as a clarification, a vertex's predecessor pointer points to the previous vertex along the shortest path. So we're going to do kind of a simple-ish example later. It kind of keeps track of where you are and where you came from, while also assessing the distance from the node you're at, and the nodes that you've passed are from the next nodes down the line. And the reason that I have Buzz Lightyear here is this algorithm actually just starts off by just saying everything is infinity, which is kind of cool. It initializes all vertex distances, vertices distances to infinity, and initializes the vertex predecessors to 0. Pushes all vertexes to a queue of unvisited vertexes. So it starts off kind of with everything is in this unvisited vertex list, and the distances are all infinite. And then it starts to kind of figure out its way, kind of creepy crawling through the graph. The algorithm then assigns the start vertex's distance with 0. So starting at A, the distance to A is 0. So while the queue is not empty, the algorithm then pops the vertex with the shortest distance from the queue. So A to BC, if B is shorter, we pop the vertex with the shortest distance from the queue. So we would pop B from the unvisited queue list. Then computes the distance of the path from the start vertex to the current vertex, so the one that we popped, for each adjacent vertex, and continues to the adjacent vertex. So it keeps kind of creeping down. If it finds a shorter one, the adjacent vertex's distance is updated. So it just finds whatever is the shortest, pops that vertex distance, and then the vertex's predecessor pointer is set to the current vertex. So that, kind of makes sense all in all, but I thought I would give an example, which I'm like 90% sure I did right, to explain this process. So we start off with, what I'm calling the visited vertex array is just empty. We haven't visited anything yet, and we set the distances to 0 for whichever one we start with, and then everything else is infinity. And there are 5 nodes. So there's 5 in total, 1 being 0, the rest being infinite. Then we start, and for here I'm saying we're starting at node 0. So we start with 0 and set the visited vertexes to 0, because now we've been there. We're kind of figuring stuff out where to go from 0. We then update the distance values of the adjacent vertices, which the adjacent vertices would be 3 and 2, as you can see here. And then the distance values to these are 7 and 1. So we pick the minimum distance, or the algorithm picks the minimum distance to 2, and then traverses down to 2, and then pulls 2 into the visited vertex array. So 0 to 2. Now that we're at 2, and we're kind of, once again, if I'm understanding this correctly, which I'm like 90% sure that I am, we still keep 3 in the unvisited queue. We know its distance, and we refer to it as well as all of the new stuff as we go, so that we can like pop back if we need to. But here we don't, because the adjacencies to, or the adjacent vertexes to 2 are 5 and 4. So here. And the distances to these are 3 to 4, and 7 to 5. So since 4 is the shorter of all of the adjacent vertexes that we have, we pop 4 into the visited vertexes, and now we're sitting there, and we say, all right, what's next? Now the adjacencies are 1 to 5, still keeping in mind this 7 to 3, but 1 is obviously shorter, and I realize I found like a cool little like node crafter thingy online, and after I made it I realized it's kind of simple in the way that I made this, so I apologize, but hopefully it still gets the point across. But we're at 4, and we see adjacent to 4 is 5 with the shortest vertex of 1, as all of the other vertexes that still haven't been popped into the current vertex situation. So we pop over to 5, and 5 is added to the visited vertexes. So now we've got 0, 2, 4, 5. Looking at the adjacencies of 5, we do all the same kind of calculations. And the cool thing about the infinite is that it helps, from my understanding of this algorithm, it helps kind of keep the info where it needs to be by saying like everything is infinite until we start assessing each adjacency and each vertex. It doesn't even contemplate the other vertexes until we continue this crawling path. So following that logic, 5 to 1, we know 1 is the shortest traversal in comparison to anything else that hasn't been popped. So we add that into visited vertexes, repeat the process for 3, and now we have 0, 2, 4, 5, 1, 3 as our final path traversal, or word I can't pronounce, traversal through this algorithm set, through this graph set. And if you add it all up, you get 1 plus 3, so you get 1, 0 to 2, plus 3, 2 to 4, plus 1, 4 to 5, plus 5, plus 1, 5 to 1, and then plus 1, 1 to 3, which gives us 7. And that's from 0 to all of the other nodes. The shortest distance is this path, and the shortest, I guess, sequence is this here, and the shortest path is this distance here. So hopefully that makes sense and clarifies things. And finally, I just want to talk about quickly the algorithm efficiency of this setup. So if we implement the unvisited vertexes in a list, kind of like I did, the runtime of this algorithm is actually big O v squared. And this is because the outer loop executes v number of times to visit the vertexes. This popping each vertex from the queue requires the big O v runtime. Then for each vertex, the algorithm goes into adjacent vertexes using the edges, so E. And this makes the runtime v squared because you're going through all the vertexes and all the edges, kind of in a quadratic format. I almost said multiplicative, but that's incorrect. And then just kind of simply, and this is just thrown in there, this was something that was discussed in the book, but if implementing using a binary heap, we can actually get the runtime down to big O E plus V log, where E are the edges and V are the vertexes, which makes sense because you've got that cool logarithmic pattern of binary heaps where it's kind of splitting in half as you go. But yeah, so that is my presentation. Hopefully it was helpful and informative, and I would open up for questions, but no one is here except for my dog. So hope everybody does well on the final, and bye.